Hello everyone, my name is Shrey Joshi, and today I'm going to be presenting to you about the aviation heat island effect. So before I tell you about the aviation effect, let me tell you about the urban heat island effect. This effect greatly affects many cities all around the world and is characterized by a large temperature gradient seen with higher temperatures present in urban areas and suburban areas rather than the rural outskirts of a city, ranging up to 10 to 15 degrees. This gradient presents itself due to the concentrated use of materials such as concrete and asphalt in urban and suburban areas, which radiates heat into the atmosphere instead of reflecting it or absorbing it. Similarly to the UHIE, the aviation heat island effect affects airports because of the concentrated use of concrete and asphalt in the runways and the terminals of the airport, allowing it, at least hypothetically, to act the same as an urban area. The guiding question was to determine how significantly do these airports, in fact, act as a center for the urban heat island effect, similar to urban areas, and how these effects can be mitigated, which this question also divided itself into the central objectives for this investigation. For this investigation, the study area was Dallas-Fort Worth International Airport. This reason being because of its unique half-moon terminal design allows for it to be an airport with the larger concrete and asphalt presence. And the large area of land that it takes up also presents its potential for future air traffic expansion of different terminals and other things being built, which would increase this footprint, which is why it is also one of the busiest airports in the United States, which is why this airport was selected as a study area. Dallas downtown was also analyzed as the urban area of comparison. Other airports include other future study areas include the busiest airports in the United States, from Atlanta all the way to Houston. To answer this research question, Landsat 7, 8, and 9 thermal data was collected. This data would represent land surface temperature. 11 and a half years worth of data was collected from January 1st, 2012 to July 15, 2022 from the U.S. Geological Survey Earth Explorer website via the machine-to-machine API with the assistance of a Python script courtesy of ERC's UHIE intern Daniel Wong. To process this data, there were two steps: pre-processing and post-processing. This bulk of data was pre-processed similarly, which made it more efficient rather than having a variety of different processing methods for different kinds of variables of data. This Landsat 8 and 9 data was processed using a special plugin called the Semi-Automatic Classification plugin in QGIS, which is open source GIS imagery analysis. Noise reduction was performed through atmospheric correction and pan sharpening, and brightness temperature in Celsius was determined. For Landsat 7, manual temperature processing had to take place due to the plugin not working as intended, and the equations were used as shown in the image. For post-processing, vector layer construction for the study area with the shapefile was created for all satellite imagery, and zonal statistics plugin in QGIS was used to determine the mean of LST, land surface temperature, and this data was exported to CSV spreadsheets. Here you can see the DFW airport from July 2012 to July 2022. You can see that the airport and its surrounding area, or the airport is significantly darker than its surrounding areas, signifying a higher temperature. The lighter areas signifies a special terminal that has a metal roof, which allows sunlight to be reflected in a lower temperature. Here are those same images zoomed out. You can definitely see the effect of climate change with darker colors on the 2022 image on the right. And then here you can see the graphs, with the blue graph representing the land surface temperature for downtown and the orange for the airport for all years. As you can see, for 2022, and 2019. These lines are very close together with only minimal differences for around 3 degrees Celsius at 3 to 5 degrees Celsius at max, depending for all the years. And you can see that it even exceeds the airport even exceeds the downtown temperatures at some points. You can also see the 2021 and 2018 symbol having this same kind of trends, with airports staying just a little bit above, maybe in some places a little bit below. You can also see seasonal fluctuations. With 2020, there was the COVID-19 pandemic, which obviously resulted in this drop in temperature due to the decrease in air traffic. And the same trend is mirrored from 2017, 2014, 2013, and 2012, with 2016 and 2015 being 2 years in which the temperature of the downtown was typically higher than the temperature of the airport, but only by less than 5 degrees. With this data, I can conclude that airports play a significant role in the urban heat island effect of the city because of the proximity of land surface temperatures between airport and downtown. And mitigation can take place through decreasing the concrete concentration of airports through adding shades on the ramps themselves close to the terminals, and adding plants or some kind of reflective material on the top, and adding active cooling systems to the runways and the tarmac itself. But more research is needed to investigate this and further verify these results. Of course, this entire project would not have been possible without the mentors of the UHIE program. Dr. C, Dr. Jiang, Mr. Femi, and Mr. Ishfaq all really helped me out in determining my area of research and helping me get the data that I need and process it. And of course, this entire SEAS program would not be possible without our wonderful SEAS coordinators, so a big shout out to them as well. Some reflection throughout this entire process. Some challenges include designing a research project, especially in remote sensing, where there's tons of data available from all different kinds of years, and essentially managing it in a way to determine a specific objective with specific processing. And of course, this huge learning curve of learning almost the entire field of remote sensing and how to process it in just about 5 weeks is very difficult to do. And I found that particularly a challenge to process 11 and a half years worth of 200 images worth of data. Best parts was I got to engage in novel research that's typically done by graduate students, and I gained long-term connections with mentors. And the SEAS program further influenced me to become an aerospace engineer, to both work and educate and during college research novel technologies and continue my research into the aerospace industry. And these are the references for this project. Thank you very much.